So I want to talk about the range of a projectile. And I've already derived the range of a projectile as an equation. I'll show you that in just a little bit. But what I want to do is approach it a different way, and that's using a numerical calculation. So let me go over the very basics of this, and then we're going to get into coding. It's going to be awesome. I'm going to have a great time. Whether you like it or not, you can't stop me. Okay, so let's say I have this ball shot at some initial velocity v0. It moves through the air. While it's in the air, there's only one force acting on it, the gravitational force pulling down. It also has some momentum on it, and remember, forces change momentum. So we have right here the momentum principle. This says that the net force changes the momentum with respect to time. I can rearrange this and solve. If I say I have the initial momentum P1, I can find the final momentum by adding this F times delta T for some short time interval. Even this works all the time here because the force is constant. But even if the force wasn't constant, I could still do this because I could choose a short time interval such that it's approximately constant. Now, the other important thing I need to know is once I know this change momentum, or once I know the momentum at all, I can use that to find the velocity, where momentum is mass velocity. I can assume that's the average velocity and use that to find the new position. Here I'm using r as the position. So I take the velocity, which is the momentum divided by the mass, multiply that time interval, add it to the old position, I get the new position. Okay, so here's how this is going to work. I'm going to start by setting up my initial conditions. I need to know it's a numerical calculation. I'm going to actually be breaking this into numbers. I'm going to break the motion into a whole bunch of time steps. Now, I'm doing this a very simple way. Okay, and you could do it much more sophisticated, but I'd like to do it this way so that everyone sees what's going on. So you start off with some initial velocity, initial position, initial time, all that stuff. Step number 1, calculate the force. In this case, it's easy because there's only one force. It's the gravitational force. 2, use that force to update the momentum. Next, update the position. And finally, update time, and then repeat the whole thing again until you get to where you want. In this case, we want to get to where the ball's back down at the ground. Now, just a reminder, I derived this. This is the range of a projectile if it is launched from the ground back to ground on flat ground. So we can use this to check our answer later, but that's just for fun. So we're going to go over here to Trinket. Trinket is a way to have Python with the visual module. There's also GlowScript, the same thing. I just like this one. So I'm going to new Trinket, GlowScript, and then so I can do blocks. Don't want to do that. I want to do this. Okay, so let's go ahead and name this projectile range test. Just range. So number 1, I'm going to set some constants in here. I'm going to use vector notation. So I can say g equals vector 0, negative 9.8, 0. I need that. And I need my initial velocity. v0 equals, let's just say 10. I don't really know. I need a launch angle. Theta equals, let's say, 30 degrees. So I'm going to say 30 times pi divided by 180. Okay. The other thing, I'm going to need a graph. Let's just do t graph equals, let's just do a function plot right now. Let's not put labels. F1 equals g curve color equals color.blue. I'll come back and fix this. Okay. Now I need to set my initial parameters for the actual object. So I need the position. I'm going to say r equals vector. It starts at the origin just because that's easier. 0, 0, 0. Oops. I need the initial momentum as a vector. So here, let's call the velocity v. And you'll notice here that there's no r1, r2, r3, because I'm just going to keep on changing this. I don't need a whole bunch of variables. So this is going to be v0 times the vector cosine theta. I should have put a picture for this. Sine theta, 0. So let's just jump back here for a second. So if I have that as my launch velocity and that's my angle, I need this as a vector. So I'm going to find the x component right here using cosine and the y component using sine, and I have no z direction. So that's my vector. And then I need the momentum. P equals m, I need m. M equals 1, P equals m times v. Okay. I need one more thing. T equals 0 and dt equals 0.01. We can change these later if we want. Okay, now how do I tell the computer when to stop doing all these loops of calculations, I need something. So let's say while r is greater than or equal to r dot y is greater than or equal to 0. Do the following. And now we're just going to do what we said we're going to do. Calculate the net force. F equals m times g. Update the momentum. P equals p plus f times dt. Update the position. R equals r plus p times dt divided by m. Now you'll notice here, like I said, I have p equals p. This is an assign statement here. So these p's don't cancel. It takes the old p and makes it a new p after it adds that. That's just the way Python and most computer programs work. And then update the time. T plus dt. And then when should you plot? It doesn't really matter. So let's just say f1.plot. You got to spell plot correctly. My x-coordinate. Let's plot the trajectory. So the x versus y position. So r dot x, r dot y, and that's it. Let's see if I made any mistakes. There's a non-zero chance that I did. Check that out. Okay, so this is working. Okay, and if you want, we can do the following. Let's print. Let's just check and see if it's working. Print x2 equals r dot x meters. This will print the position at the end. And then let's say xc, or let's say range, no, that's a xr, is going to be equal to, using the equation, it was v0 squared, so I'm going to say v0 squared times sine of 2 times theta divided by g. Now I can't divide by g because g is a vector, so I'm actually going to divide by the magnitude of that vector, like that. And let's print. Theoretical range xr meters. Okay, let's check that out, see if it runs. I'm kind of nervous. Okay, it worked. Check that out. We don't get the exact same thing. The reason is that we're taking small time steps, and so if you want to make this smaller or bigger, you could. If I make this a smaller time step, it's going to be a more accurate calculation. But you know, good enough. It's good enough. So I don't even need to worry about that. Oh, and also there's one thing here. This actually does, once this gets to, that actually moves lower than 0 because it goes through and calculates the position, and if it's lower than 0, it prints it. But it already did the calculation. Okay, so that's just one of the things. Let's put this back up like that. Okay, so we're cool. We could use this to change the angle and print the range and all that stuff. I don't really even need to print out the trajectory. That was just to make sure things are working. Okay, now I want to calculate the maximum range this way. So let's do this. I'm going to change stuff up. And I'm going to take some shortcuts that aren't necessarily the best thing. So let's go up here and say def x range. Let's define a function. So I'm going to input an initial velocity and an angle. I'm going to assume it starts from position 0, 0, 0. So I'm going to say v0 and theta. And then I'm going to move all this stuff. Let's just cut that. Tab, indent it. Oops, I didn't indent. So now this loop is in the function. I don't want to put that there. So I need to put this stuff in there too. Let's just move it all in there right now. Let's get rid of F1. Let's get all this stuff in there. Indent it. Indent, indent, indent. Oops. Okay, so you see here that I don't say what theta is. I don't want to do that. I don't want to say what V0 is. I want to input them in over here. And let's do these spaces. So let's just check and see if this function works. Oh, this needs to be indented. Okay, and then I'm gonna, over here, once that loop finishes, I'm gonna return r.x. r.x is the x component of the position. So over here, I can say, for the theoretical, I'm gonna say, put this in as 10 and 30. I'm gonna change this to 30. 30 times pi divided by 180. That's the theoretical. And this is going to be, I don't have r.x. I'll just say xc for calculation. xc equals x range. 10 is my velocity, and 30 times pi divided by 180 is the input. So this function up here makes it all the calculation up there. I can change these values and print it out over here. Let's just see if it works. It won't make a graph, but okay, it's working. There we go. Okay, so now you could see I could easily just change this to 20, and it could rerun it. And I get a new value. That one didn't change. Okay, we are golden here. Let's make a graph. So I can put it up here. T graph equals graph. The X label, X title. I want to plot the range at different launch angles. Okay, so I'm going to say the x-axis is going to be, X title is going to be launch angle. I'm going to put it in degrees. I can't spell. The EG, and the Y title is going to be the range in meters. And then I need a graph. F1 equals G curve. I deleted this. Color equals color.blue. And I should put a title. Let's use a velocity of 10 degrees. So what we're going to do down here is I'm going to make another loop. I'm going to start off with an angle t theta for temp theta equals, I don't want to launch it at 0 degrees. Let's launch it at 1. 1 times pi divided by 180. And my velocity, t v0 equals 10. And I'm going to say, while the angle is less than, I'm going to go to 89 degrees. While t theta, oh, I need a d theta too. D theta, that's how my step size is going to be the same. It's one degree. Let's do 5 degrees. 5 times pi divided by 180. I don't know why I always think in degrees instead of radians. While theta, temporary theta, is less than 89 times pi divided by 180, do the following. The first thing I want to do is calculate the new range. So t range is going to be equal to x range. I'm going to put in tv0 for the velocity, and I'm going to put in temp theta for that. Now I'm going to plot f1 dot plot. My x value is going to be equal to t theta. I want it in degrees, so I'm going to say times 180 divided by pi. And then my y value is going to be the range, t range. Now I want to update my angle. So I'm going to say the temporary theta, t theta, is equal to the same thing, plus d theta. So now I've increased it, and then I'll just keep on doing this forever, and I should get a nice graph of range versus angle. And I don't think this will work because I probably made a mistake somewhere. And it worked. Look at that. Okay, that worked. So look, where is the maximum range? It's right here, 45 degrees. Check that out. Okay, now you may think this is the stupidest thing ever. Why would you do it this way? You're making it way too complicated. No, because I have given you practice in using functions. I've given you practice in how to make a numerical calculation quite simply, right? We're not doing super complicated stuff. This is just normal stuff. And finally, I found the range for this particular case. Because what if I launch this off of a hill? What if I launch this on a sloped hill? What if I launch this with air resistance? The same way in a lot of those cases, especially with the air resistance, finding the range, you almost have to do it this way. Okay, you can't just figure it out other ways. So there you go. Practice with the projectile motion. Hope you enjoyed this. I had fun. So even if you didn't have fun, don't worry, because I enjoyed it. And I'll talk to you guys later.